Students, today we are going to see about the type of solvents. Number of solvents available depends on the properties that is classified. So here polar solvents, non-polar solvents and semi-polar solvents. These are the main classification. In this, polar solvents are further classified into two types. One is protic solvents, another one is aprotic solvents. Okay, we'll see what is polar solvent. Okay, so whenever the compound, the given solvent is having the large dipole moment, that kind of solvent is called as polar solvents. Okay, that is highly polarized. Those solvents is called as polar solvents. So here dipole moment is huge, the charge is high. Well, going for that further classification of polar solvents, there are two types. One is protic solvents, another one is aprotic solvents. Protic solvents always form the hydrogen bonds, readily form the hydrogen bonds. That means there is a partial electronic charge and partial positive charge from the solid particle will be possible to interact and form the strong hydrogen bond. This hydrogen bond is the responsible for any kind of making a solution and responsible for solubility. Okay, for example, methanol is the polar solvent. The reason is that dipole moment is the large, and at the same time it will make the hydrogen bond. That's why it is coming under the classification of polar and call it as protic solvent. We can say polar protic solvent. Okay, the second classification under the polar solvent is aprotic solvent. Aprotic solvent is coming under the, there is no possibility of hydrogen bond formation. Example, tetrahydrofuran. What is the structure of furan? 5-member ring. In that cyclohexadiene, in that oxygen atom is present, that is furan. So in this case here there is a no double bond, so it is called tetrahydro with oxygen atom. Hetero atom is available in the 5-member ring, so it is called tetrahydrofuran. In this THF, people used to call it as THF as a solvent, right? Tetrahydrofuran is one of the solvents, is coming under the category of aprotic solvent because there is no possibility of formation of hydrogen bond with the solid molecule. Okay, but other cohesive forces are available. What are the cohesive forces? The one is the weak intermolecular force of attraction, that is van der Waals interaction, hydrogen bond, ion-ion interaction, dipole-dipole interaction, dipole-induced dipole interactions are available. This together is called as cohesive forces. Okay, in the aprotic solvent particularly no hydrogen bond. If we come into the picture of non-protic solvents, here molecules whose electric charges are equally distributed. For example, carbon tetrachloride, if you take, what is the formula for carbon tetrachloride? CCl4. Yes, CCl4. Here all the chlorine atoms are highly electronegative, right? Usually the chlorine is highly electronegative. Here all the chlorines and all the corners are equally pulling the electron, so that dissociation of the electrons are equally distributed. Then the overall dipole moment charge is cancel each other, so mu is equal to, that means dipole moment is equal to, what is it? 0. So that is called non-polar solvents. So it will form the hydrogen bond because the chlorine atoms, all this kind of electronegativity atoms are existing in the solvent and readily form the hydrogen bond with the solid molecule, which is responsible for solubility. Okay, if we come into the third one, semi-polar solvents. What is semi-polar solvents? That is partly polar molecules. So that is, for example, acetone molecule if you take, because of the carbonyl group existing in between the two methyl groups, that carbonyl group in this oxygen atom is pull the electron and the localization will be happen. Because of that, that partly polarization will be happen, that readily interact with the solid molecule and produce the, and will go for the solubility and produce the solution. Okay, these are the type of solvents existing in the solvent component. Next, solid solvent interactions. So why or reason for solid solvent interactions in different solvents? If I take polar solvents, if I take non-polar solvents, if I take semi-polar solvents, if I take aprotic solvents, so incoming solid molecule interact differently because there is some places hydrogen bonding existing, some places the dipole moment plays important role, some places non-hydrogen bond plays an important role, some places van der Waals interaction plays an important role. So this solid solvent interactions, it is very important for the solubility. Okay, for example, polar solvents, if I take example, what are the solvents? Are polar solvents? That is the high dipole moment, right? So the one is the reason for polar solvents. What are the properties are coming under the polar solvents? One is high electric solvent, the solvent should have the high dielectric constant, that is denoted as epsilon. Then another one is ability of breaking covalent bonds. The incoming solute molecule may be the crystal structure or non-crystal structure, whatever the compound is incoming component, that is the solvent has the ability to break the covalent bonds. The third one is they readily form the hydrogen bond with the incoming solute molecule, then the possibility of solubility will be happen. Okay, example, water, H2O, the oxygen is ready to donate the electron and ready to form the hydrogen bond, and this hydrogen atom in the water molecule is also ready to make a hydrogen bond with the incoming solute molecule and make a strong solute solvent interaction and possibly happen the solubility. Okay, the second one is non-polar solvents, that means no hydrogen bond formation here. Okay, here only dissolved non-polar solids are possible and form the solution. Example, benzene, hexane, these are the examples for non-polar solvents. The third category is semi-polar solvents. What are the semi-polar solvents? Example, acetic acid, pyridine, these are the example for semi-polar solvents. Okay, so solvents act as an intermediate solvent, induces certain amount of dipole moment, slight amount of dipole moment will be induced, which helps in solubility, helps in solubilizing the incoming solute molecule in solvent. This is coming under the semi-polar solvents. Okay, so what kind of compound will dissolve in which kind of solvent? That means like dissolve like, the same kind of behavior component will like the same kind of behavior of the component, right? That we can simply say like dissolve like, that is polar solvent dissolves polar solid, non-polar solvent dissolves, yes, non-polar solid. Okay, so these are the reasons for solid solvent interactions in different solvents. Okay, the solubility is directly proportional to solid solvent interactions, right? That's what we explained in the mechanism part. That means solid solvent interaction is increasing, then solubility automatically goes up. Okay, the next to the solubility, there is another component is called ideal solubility parameters. Before to enter into the picture of ideal solubility parameters, we will look into the ideal solution. What is ideal solution? If I take the two mixtures, two components A and B at a given temperature and pressure, the volume of ideal solution is equal to the sum of the two components at given temperature and pressure is called ideal solution. What is ideal solution? I am repeating again, at a given temperature and pressure, the volume of an ideal solution is equal to the sum of the two of the volumes of its pure components at the temperature and pressure. Okay, this ideal solution, so what kind of solutions are called it as ideal solution? What are the compounds or what are the solutions are following the Raoult's law? If the solution is following the Raoult's law, such solution is called ideal solution. What is Raoult's law? We will see in the forthcoming slides. Okay, within few minutes we will look into that. We will talk about the Raoult's law and their definition and equations. Okay, if we come into the next point, if solution shows deviation from Raoult's law, then it is called as, there is a two possibility of deviation. One is positive deviation, another one is negative deviation. So if the solution deviates from either positive deviation or negative deviation, that kind of solution is called as non-ideal solution or real solution. Okay, so deviation from the Raoult's law, we said one is positive deviation, another one is negative deviation. In such cases, in such type of environment, that is, it may be increased solubility due to hydrogen bond whenever the deviation is negative. If the deviation is negative, it may be increased the solubility due to hydrogen bond formation. If the deviation is positive, it leads to decrease the solubility due to the formation of polymer compound. That means it not forming the any hydrogen bond. It's not favor to the hydrogen bonds. So negative positive deviation leads to decrease the solubility. Okay, so next one is positive deviation in most cases due to the difference in cohesive forces. What are the cohesive forces? All intermolecular interactions, hydrogen bond. Okay, then another one is dipole moment and van der Waals interactions. Those interactions or forces are coming under the cohesive forces or internal pressure of the molecules of each constituent. Okay, so ideal solubility parameters in this topic. If you want to estimate the ideal solubility parameters, there are several equations are available and proposed by the various scientists. Here, one particular scientist, Joel H. Hildebrand, he proposed or he given the equation to calculate the ideal solubility parameter. Okay, so to estimate the ideal solubility parameter, we can use this Joel H. Hildebrand equation, that is delta 1 is equal to root of delta U by V. What is delta U? What is the U? U is the internal energy. Sometimes we are expressing in terms of E. E is also internal energy. How the molecules are getting the internal energy, that means it getting the internal energy through rotation, vibration or translational. In this way, the molecules are gaining the internal energy. We are expressed in the terms of E or U, that is called internal energy. Here what is V? V is the molar value. Okay, so in thermodynamically speaking, how can we write the equation? How can we give the equation for enthalpy? H is equal to, yes, E plus PV, or E is nothing but U. We can produce the terminology E or U for the internal energy. So delta H is equal to delta U plus PV. So in ideal gas condition, what is the terminology for PV? PV is equal to nRT. If I take only one gas, if I consider, then N become 1. So PV and can be replaced by RT. So if I change the equation accordingly, delta H is equal to delta U plus PV or delta U plus RT, right? If I replace the U value in the equation, delta 1 is equal to root of delta U by V, then we can get delta H minus RT by V root of, overall root of, right? This is the Hildebrand equation to find out the solubility parameters, that is ideal solubility parameters. So where delta 1 is solubility parameter, delta U is molar energy, V is molar volume of solvent. So delta H is the molar heat of vaporization of solvent, R is the gas constant, T is the temperature. So the difference between delta 1, that is solvent solubility parameter, delta 2 is the solute solubility parameter. The difference between the solute solvent solubility parameters is, we can identify the numerical value of solubility. Okay, then another one, what is the parameter, that means conventional unit for solubility parameters? We can express the unit for solubility parameters in two different ways. One is root of calories per centimeter cube, or in SI units we can express joule power 1 by 2 and meter power minus 3 by 2, or overall root of joule by meter cube overall root of, right? Root of joule by meter cube, that is SI units of ideal solubility parameter. Then what are the other methods are available to measure, or methods available to determine the solubility parameters? Here one method is Small's method. So what is the expression? Delta is equal to rho summation of F by M. This is the equation to find out or determine the solubility parameter. So the method is Small's method. Here delta is solubility parameters, rho is density, F is sum of heat of evaporation of atoms and groups, and m is molecular weight of the given compound. So this is the Small's method equation. And Hoy's method equation is delta is equal to rho summation of Fi divided by molecular weight. Okay, all the terminology is already explained in the Small's method. Another method is Hansen method. Here the equation is delta T squared is equal to delta D squared plus H squared plus delta P squared. Okay, that is, some people are representing this delta rho squared. We can use either P or rho. So here delta T is Hansen's total solubility parameters. Okay, so it is present and is together is called delta D is energy from dispersion forces between molecules. What is dispersion? When the solute molecules are dispersed into the solvent, that is called dispersion. Okay, so during that time number of cohesive forces are acting into the picture in the solution. Those things are called dispersion forces. Delta H is the energy from hydrogen bonds between molecules when solute interaction, or when solute molecule are entered into the solvent. There are three possibility of interactions. What are they? Solute interaction, solvent interaction. The third one is very important, that is solute solvent interaction. Okay, so here delta H is the hydrogen bonds between molecules. The delta P is energy from dipolar intermolecular forces between molecules. Okay, dipolar, that means polar nature, dissociation of the given solute molecules is called dipolar intermolecular interactions. Okay, three parameters in three dimensions called as Hansen space. What is Hansen space? There are the three dimensions, x, y, z directions. There are three parameters are available, and another one is in Hansen space. If the molecules are very closer and likely to possible to make a miscible compounds or make it soluble each other. Okay, then relative energy difference of the system. How can we calculate the relative energy difference? What is the use of this relative energy difference equation or formula? So this equation or this formula helps us to identify the given solute is soluble or not soluble or partly soluble. We can identify in order to get once we get the answer or once we solve this formula. Okay, what is the formula? RED, relative energy difference of the system, is equal to RA divided by RO. What is RA? Distance between Hansen parameters, right? It is Hansen parameters in three dimensions. Then RO, what is this? Interaction radius. That means the one particular atom in this two radius, what is the distance between the two radius is called RO. Okay, so what are the things? Once we get RED is greater than 1, suppose that compound that is not dissolved in the given solvent. If RED is equal to 1, then possibly partly dissolve the given solute in the solvent. The third one is if RED value is less than 1, then the given solute molecule dissolve in the given solvent. Okay, so this is the use of RED value. That means relative energy difference value using this formula. Okay, what are the applications of solubility parameters? Several applications are available for the ideal solubility parameters. The first one is to predict the solubility parameter behavior of solvents. The second one helps to find the compatible solvent for polymers, because to dissolve the polymer compound in the solvent is difficult. So we have to choose the right solvent for the polymer compounds in order to dissolve the compound. For this purpose, we are using this ideal solubility parameter. The next one is in the selection of co-solvents. Sometimes solute molecule is not soluble in the given solvent. So during that time, we can use the additional solvent in order to enhance the solubility. Okay, so for that purpose we are using the co-solvents using this ideal solubility parameters. The fourth one is prepare the polarity scales. Right side I have given the polarity scale of each solvent depends on the solubility nature of or depends on the solubility of the given solute molecule. Okay, so we can prepare the polarity scales using this ideal solubility parameters. The another one is we can use chemical kinetics determination. Okay, chemical kinetics for the rate of the compound, the rate of solute dissolved in the given solvent. So chemical kinetics also we can calculate, we can identify using this solubility parameters. The another one is finding suitable drug formulations. Various, we can take the drug molecule and we can use this, we can prepare the formulations based on the ideal solubility parameters. Then enhance the poorly water soluble drugs. If any drugs are poorly water soluble, then we can get to know about the ideal solubility parameters. Then we can think about, or we can do it for enhance the solubility. Then guide to choose the better solvent for the solute. Yes, because like dissolves like, right? This is the main concept of the solubility. So we can guide to choose the better solvent for solute molecule and establish the SAR. That means based on the solute we can choose different solvent and we can map up which solute molecule dissolve in which solvent. That is the meaning of here SAR, structure activity relationship. That means based on the solute structure we can choose the right solvent, because hydrogen bond need to be formed or other intermolecular forces need to be evolved in this particular concept of solubility for the given solute molecule. Okay, then it is also the solubility parameters is also applicable or applied in the cosmetic industry, paint industry, pulp industry. In several industries also we are using this ideal solubility parameters. Okay.